Hi, I'm Stijn Omus, and today's lesson will be about the size of a sphere, something like this. And the question is whether we can get that size from just one photograph, and the traditional answer is no, but we're going to use a trick. And it's going to be in three parts. First of all, I'm going to derive a formula for the radius of a sphere, and the trick is to put it on a plane, on a horizontal plane. Then I'm going to test the predictions in an experiment with real spheres and real cameras with a photograph. And I'm going to measure the diameter with an apparatus like this called a caliper or caliper, I don't know. And finally, I'm going to compare the visual predictions with direct measurements with that caliper. So if we have a sphere, and a red one, and it projects onto an image plane, then the question is, can we get the size from the photograph? There is, in this case, a round projection on the image plane, and do we know enough to get the size of the sphere? And in an earlier lesson, I told you about visual spread. So the visual spread P is A over D. So we only know when we can measure P from the photograph, but we only know the proportion of size and distance. So we do not know the size. Well, we can use a trick. We can take two photographs, also called stereo. And if the base, the distance between the cameras, E, is known, then we can make some calculations. But I'm not going to do that today. That's for a future lesson. The trick today will be to put the sphere on a horizontal plane. And the assumption, an important assumption, is that we know the height of the camera, in this case h, and of course everything is in quadrances. And let's see what we know, or what kind of quadrances are in this configuration. Well, we have h for the height, A for the radius of the sphere, but also for the height of the center of the sphere from the ground plane, from the horizontal plane. Then we have D, which is the distance between the viewpoint and the center of the sphere. And finally, X is the distance on the plane between the foot of H, the vertical, and the point where the sphere touches the plane. We have two spreads. P is the visual spread, I talked about that earlier, and S is the sort of direction spread. So from the downward direction to the center of the sphere. When we put that all together, we know the height of the camera, that's the assumption, and we can measure the spreads. So D and X we don't know, but turns out we don't need to know that. But what we want to know is A, the radius. So just a quick word about diameter, radius. I use that, all those terms. So the diameter is, when I put my fingers like this, then the separation of my fingers, that's the diameter of this little ping pong ball. The radius is from the center to every point on the sphere. And D is twice R. We can also express the radius in quadrants. Quadrant A, that's what we're going to do in the derivation. And A is R squared. But sometimes we need the diameter, so the diameter is twice the square root of A. So then we are okay with these terms. Now, let's go and derive the formula. So I'm taking a side view here and I make it a little cleaner. So the same quadrants as earlier, and that's why the same two spreads. Now we can lift the X up so that there is now a right triangle, X, D, and G is a new quadrants. And then on the left and on the right we have A as the sort of the basis of that X line. And of course we still have H, which is the entire, the height, the quadrants between the viewing point, the red point, and the horizontal line. Sorry, the horizontal plane. So let's go over some things that we know. We know the visual spread P. It's simply A over D. We can go to the other right triangle, G, X, and D. And then we have the spread S, and that's the opposite quadrants over the hypotenuse quadrants, so X over D. And we also know, because of Pythagoras, is that G plus X is D. So if we simplify X, or express X is S times D, then we can apply a Pythagoras, and it's G plus X is G plus SD is D, and now G is simply 1 minus S times D. We still have the P is A over D, so let's combine that. So now I'm expressing D as 1 over P times A, and fill that in, and then we get a simple expression for G, and note that the X and the D are gone, so we don't need them anymore. So now we're going to focus on those G, A, and H. So in classical trigonometry, you can simply add the two line segments to get the larger one. But this is rational trigonometry, so we're going to use the triple quad formula. And this is the triple quad formula, or an expression. There's also symmetric waves expressing this, but here it goes. So G plus A minus H all squared equals 4 times G times A. Now we already have an expression for G, so let's fill that in. And then we get this long expression. And let's make the expression bigger and the diagram smaller. So here it is. And this is the solution. So note that radius A is something times height H. So the overall form is pretty simple. And the proportion that you see there, the numerator and the denominator is an expression in P and S. And it's not that complicated. So if you keep in mind P and 1 minus S, it's an expression P times, big thing in block quotes, P plus 1 minus S, plus or minus, I'll come back to that, P times 1 minus S, and then take the square root of that. And then the denominator is P minus 1 minus S all squared. So let's look at that plus or minus. And it turns out that it depends on whether H is larger than A or vice versa. In our case, H is larger than A, and also in the experiment that will be the case. And then you need a minus sign. So back to our original configuration. So we now have an expression for the radius A of the sphere. And we assume that we know H, the height of the camera, and from a photograph we can measure S and P. So let's do that. So I put 5 spheres or balls on the floor here, together with an A4, and that's relevant because I am using the A4 for the height of the camera. You can go to another lesson to understand that. And in my case, it's the camera is on my desk and it's here on the floor in my office. And the height turned out to be 75 centimeters and 4 millimeters. And I'm measuring, as I said, with this caliper of which the batteries died. And here are the prediction and measurements. First, the measurements with the caliper. So it's pretty precise in the sense that there's 2 decimals expressed in millimeters. So the smallest, this one, the smallest sphere is 32 millimeters, 85. So that's pretty precise measurements. The next one up, I use the white one, the ping pong ball. It's 40,21. And then I used, that was Christmas decoration. It's 59 times not times, 59,51 millimeters. So that's very precise. Then I have some styrofoam spheres, and I bought them in a hobby shop. And I cannot measure that with a caliper, so I'm trusting the shop, and they gave me 10 centimeters and this one 12 centimeters. So not that precise. So now let's go to the predictions. The first three I'm using also the high precision for the prediction, and then for the large and the extra large ball or sphere, I'm using just millimeters. But let's look at accuracy. So what is the difference between the prediction and the measurement? And the difference is really small. So for the smallest, this one, it's 0.31, oh, there goes my ping pong ball, 0.31 millimeters. And the ping pong ball that just fell on the floor, it's even a difference of 0.02 millimeters. So 2/100ths of a millimeter, which is amazing. And then the medium sphere is 1.68, so it's almost 2 millimeters difference. And for the larger ones, it's 2 and 1. So that's pretty good. And now I want to see what a correlation is. So I expressed it on the x-axis, it's the measurement with the caliper. And on the y-axis, there's the prediction with the formula. And I'm fitting a straight line through those 5 measurement points at 5 times the measuring and predicting the diameter of the sphere. And I get an R squared of 0.999671. Really, really amazingly high. So what do we have? I derived quite a simple formula, again, as we've seen in earlier lessons, for the radius of a sphere from knowing the height of the camera and measuring 2 spreads. And again, rational trigonometry allows me to express this in a really simple, or quite a simple formula. Depends on your taste whether you think this is really simple, but I think it's quite simple. But more importantly, because we're not just interested in the mathematics of this, I'm also interested in, is the prediction actually true? So I showed you a photo of 5 spheres on the floor, and I measured the diameters in a separate way directly. And the predictions are very accurate. So this is very nice result. And I think I want to stress that. So as much as I like the geometry and I like the algebra that comes out of it, the real test, of course, is in an experiment, whether it makes really good predictions, and it does. So I'm really happy with that. All right, thanks for watching. If you if you have a question or a comment, you can put them down below. Or if you want to contact me directly, you can go to my website, and then there's a contact form there, and you can ask me questions directly. All right, bye-bye.